The other day, we were looking at making the transition from solving all types of equations where if we had solutions, they were all within the real number system. And the other day, we crossed over into the complex number system. And what I'm going to do here is just look into from page 81, okay, just the first three items I said to be looking into. And I thought I would kind of fine-tune things in terms of looking at terms within the complex number system. Okay, and now for what we have in terms of equations that will end up as complex roots, we have on page 57, okay, we have something that is going to run as a bit of an analog to previous items we've looked at in the case of working with quadratic equations, but where we're going to end up with complex roots instead. And again, with complex numbers, okay, we have at the foundation, okay, we have the letter I, which will be in reference to the square root of -1. And once you square both sides, okay, we have that I squared is equal to -1. Now, for what we have in the case of number 57, we're looking at solving for u, whereupon we have 4u squared plus 64 is equal to 0. And okay, so for what we have here, we can isolate the variable term. Okay, so we have a binomial of addition with 4u squared plus 64, and say that if I isolate the variable term, okay, so I can take 64 away from both sides. And so to the left, 64 and -64 will cancel out. And to the left, I'm going to have 4u squared. And to the right, I have -64. And isolating u squared, okay, so we have 4u squared over 4 is equal to -64 over 4. And 4u squared over 4, this will go to u to the second. And -64 divided by 4. Okay, so we're going to have at -16. And okay, so for what we have right now, okay, we have something that is going to run the course of where the follow through, okay, we can operate in lines with the square root property of equality. And when we looked at the first encounter, okay, this is where in the real number system we had p to be a non-negative value, and if we had that the square of x or whatever variable is involved is equal to a constant, then we have two pathways to which the variable is going to be equal to. Okay, in this case, you have plus or minus the square root of p. And in this particular instance, okay, we have x squared represented by u to the second, p by -16. And looking at going from u to the second to u, and we have is equal to plus or minus the square root of -16. And now for what we have in terms of the values, okay, now in the real number system, you're not going to have the square root of a negative, but you will in the complex numbers. And now the square root of 16 becomes 4, but in the case of the square root of -16, okay, we're going to have complex roots. And so for plus or minus the square root of -16, we are going to have plus or minus 4i. Okay, and so we have for the roots in this case, right, they're going to be additive inverse complex numbers with 4i as well as -4i. Okay, so we have complex roots exclusively, and we will encounter equations that will have a blend of both real values and complex numbers. Now, for what we have in the case of what we have for number 58. Okay, so we got this time going from the variable u to the variable p. Okay, whereupon we have 8p squared plus 72 is equal to 0. All right, and now we have 8p squared plus 72 is equal to 0. And let me pause. Okay, I could divide the whole equation by 8. And I could have divided the whole equation by 4 and just have, in terms of just the square of the variable. But again, just like earlier, I'm just going to wait until the later stage of dividing by the number that is in front of the squared variable. And so we have with 8p squared, I'm going to get this by itself, undoing addition, and this time where I am taking away 72 from both ends. And so we now have 8p squared is equal to negative 72. And we have with division by 8. Okay, so I have 8p squared over 8, so this will become p squared. Then we have p squared is equal to negative 9. And again, with the square root property, okay, this time we have p squared equal to negative 9. So we're not looking at the same kind of p, because you had the p squared is representing x squared. And so p squared going from p squared to p, and the formula p is represented by negative 9. And so I have p is equal to plus or minus the square root of negative 9. And once again, we have complex roots. Now, the square root of 9 is going to be 3. But in the case of negative 9, okay, we're going to have at 3i. Okay, so two numbers will square into negative 9. And both of these, again, will be complex roots. And we have plus and minus 3i. So we have itemizing, so we have p equal to possibly negative 3i or positive 3i. Okay, now, okay, so for both of these situations, okay, we've had the utilization of the square root property of equality. Now, for what we have in the case of number 61, okay, we're going to have to create a different pathway to find out the solutions in this one. And in 61, okay, now we've got t squared minus 8t, okay, and we have is equal to negative 24. So we have a quadratic equation, and this one is not yet established in standard form. And so setting this equation to 0. Okay, so I can move the constant from the right over, okay, by adding. And we're going to have in standard form, now we're going to have t squared minus 8t plus 24 is equal to 0. And one might try to factor this trinomial into integer coefficients. And if you factor out t squared, you have t times t. But we're going to have a bit of a problematic situation, because if you try to multiply two numbers into 24 and have them to simultaneously add to where we come out to negative 8, okay, we're not going to have this possible, okay, because you have like combinations like negative 24 times negative 1, that's positive 24, but the sum of those constants would be negative 25. Okay, think of another set like negative 12 and negative 2, but those constants add up to negative 14. And if you get a bit closer, you have like negative 6 and negative 4. Okay, so you have like negative 10 is the sum. Any other combination in the integers that are negative, you have negative 8 and negative 3, but that combination adds up to negative 11. So there's none among the combinations that will add up to -8. Okay, so in terms of any recourse in terms of solving, so we don't have the direct pathway to utilizing the zero product property. But what we can use, okay, is the quadratic formula. Okay, so we have just identifying, okay, the a, b, and c coefficients. Okay, so t squared, okay, we have at 1t squared. And for b, okay, that is the middle coefficient or the first order variable coefficient. In this case, we have b at -8. And c, okay, we have at 24. And setting things up, okay, so we have with t, we got -b plus or minus, okay, the square root of b squared minus 4ac. You have all over 2a. All right, so I'm not solving for x, but I'm solving for t, and we have the same basis in terms of the quadratic formula setup. And entering the substitution realm, okay, so we got -b. Now b is a negative value, so I'll be looking at taking the opposite sign of -8. And we have plus or minus, okay, the square root. And for b squared, okay, so you have the square of -8. And for minus 4ac, so we have minus 4 times 1 times 24 you have all over 2 times a. Okay, so this will be 2 times 1. Okay, so the only thing I've done is just replace a, b, and c with the numbers that they are set equal. Okay, so now looking at specifying, so you have -b. Okay, this translates to +8. We have plus or minus. Okay, we have the square root. Okay, and being careful with the signs. Okay, now for the square of -8, square of -8 is going to be 64. And we have minus 4 times 1 is -4. -4 times 24 is going to be -96. And we have all over 2. Okay, now we got 8 plus or minus the square root, okay, of -32. And we have all over 2. Okay. Now for the square root of -32, I'm going to lower this in terms of reduced radical form. Okay, so we've got for the square root of -32, and we can just take out the negative part, so you have like the square root of 32 times the square root of -1, and you can just go ahead and write this as the square root of 32 times I. Okay, now 32 is not a perfect square value. Okay, and now for what we have in the perfect squares, 1 squared is 1, you've got 2 times 2 is 4. 4 will go into 32, but if I up the ante, okay, we got 3 squared is 9. 9 does not go into 32. What about 4 squared? Well, 4 squared is 16. 16 goes completely into 32. 5 squared is 25. And once I get to 6 squared, which is 36, I'm past the number 32. So we got perfect squares that will go into 32. We got like 1, but this really does nothing for us. 4 will go into 32 8 times. But in terms of reducing the amount of simplification involved, 16 is going to be the highest value divisible into 32. So I have the square root of 16 times 2 times I. And separating, okay, so I have the square root of 16 times the square root of 2 times I. And so we had the square root of 16 is 4. And you have times the square root of 2 times I. Okay, and so rewriting, okay, in this ratio, so we now have 8 plus or minus, and for the square root of negative 32, okay, we're going to have 4 times the square root of 2i, and you have all over 2, and what I can do here, notice we have even valued leading coefficients. What I'm going to do here, I'm just going to split up these terms. Okay, so you have 8 halves, okay, which will be at 4. And we have for 4 times the square root of 2i over 2. Okay, now 2 will go into 4 2 times. And so we have 8 halves is 4, and we have plus or minus. Again, 2 into 4 is 2. Then we have attached, we have 2 times the square root of 2 times I. And if you separate the terms, okay, so you have 4 plus 2 times the square root of 2 times I. Now I is outside the radical. Okay, so you have 2 times the square root of 2i. And also we have 4 minus 2 times the square root of 2i. And just another notation. I think Alex will pick this up as well, but I think it's more accustomed to having I at the end. But another way of writing would be just have I in front of the radical. So one combination you have 4 plus 2i times the square root of 2, and we have 4 minus 2i times the square root of 2. Okay, that's another notation for the complex numbers. But in both formats, okay, I is not going to be inside the square root radical. All right, and we'll get back into equations, but since we were kind of fresh off of just looking into complex numbers, I just wanted to just mention some things about the immediate terms where we have just translating, like going from square roots of negatives to the letter I, and looking at some of the introductory operations that involve complex radicals. And again, we have with I, we have the square root of negative 1, and we have the I squared is equal to negative 1. And for the standard form of a complex number, okay, so I have a plus bi. Okay, now just some words here regarding operations. Okay, and these are some of the heuristics of working with complex numbers. Okay, whenever you're looking at operating, say when operating with complex numbers, or in this case when we're operating with complex radicals, go ahead and write the radicals in terms of the letter I. Okay, so whenever you're working with complex radicals, go ahead and write the radicals in terms of I, and that is to assist one from performing any careless mistakes. And let's say that if you have simplifying, and we'll say just first instance, okay, now say operating with complex radicals. Now you might have a couple of complex radicals where you can say we have the square root of 9 times the square root of -4. And this part is going to stress especially going ahead and writing the radicals in terms of the letter I. And a common mistake that can occur, now we have square root terms, and the temptation will be to multiply -9 and -4, and a negative times negative is a positive. In this case we would have 36, and recalling the principal square root rule, and so well the square root of 36 is going to be 6. Okay, now the pathway to solving or arriving at the solution, namely the product of the square root of -9 and -4, is not going to be through the aforementioned route. Okay, what we're going to do here is that with the square root of -9 and the square root of -4, okay, we're going to write these in terms of the letter I. Okay, and so for the square root of -9, okay, that is going to be at 3i. And for the square root of -4, okay, square root of 4 is 2, but the square root of -4, okay, that is going to be at 2i. Okay, so got 3i times 2i, and 3 times 2 is 6. Now we have the I times I is going to be I squared. Okay, and just going back, okay, notice we have I squared is equal to -1. Okay, so with I squared at -1, okay, so 6i squared becomes 6 times -1. So for the product of these radicals, okay, this will come out to -6. Okay, now another case here. Now both -9 and -4, those were the negatives, perfect squares. And let's say if we have something like the square root of -20, and we have times, okay, the square root of -5. Again, anytime you see square roots of negatives, go ahead and extract the letter I. Okay. So we have in this instance, okay, so for the square root of -20, you could simplify the radical, but we'll just kind of put this on hold for right now. For the square root of -20, okay, we have the square root of 20 times I. And for the square root of -5, okay, we have the square root of 5 times I. And what I'll do here, okay, so you got, I can multiply the radical terms together. Okay, we don't have any negatives inside. Again, anytime you have negatives, go ahead and extract the letter I. Just going to mention, okay, so just putting the radicals, so you have square root of 20 times the square root of 5. I times I becomes I squared. Now we got the square root of 20 times the square root of 5. Both of these are positive, and I can just cluster together 20 and 5. 20 times 5 becomes 100. And I can go ahead and write I squared is negative 1. Okay, so we have the square root of 100. Square root of 100 is 10. I squared, okay, so that is negative 1. And for the final dismount, okay, we have 10 times negative 1. Okay, that is going to be at negative 10. Okay, so this is what we're going to have in this case. All right, now in terms of what we have, okay, for division, okay, and again, you're going to extract, okay, the letter I, okay, and for what I have here, okay, so if I have, for instance, okay, the square root of negative 54, now I'll show you a couple of ways of going about this. Okay, so I have the square root of negative 54, and we have over the square root of negative 6. Okay, all right, so we got here, give me just a moment. Okay, so you got the square root of negative 54 over the square root of negative 6. So you have square roots of negatives. And if we go ahead and extract the letter I, okay, so again, I is outside each of the radicals. And I'll just take this one step further. Okay, so you have a common factor in the numerator and denominator with the letter I. So just go ahead and get those to cancel. Now in terms of the follow through, okay, now I've got the square root of 54 over the square root of 6. And so I got positive numbers, and what I can do here is that, kind of like with the multiplication, I can cluster together what I have as the square root of 54 over 6. Square root of 54 over 6. Now 54 over 6 is going to be the square root of 9. And in turn, okay, the square root of 9 will be 3. I'll show you another. Let me just show you this. Okay, so for the square root of negative 54, over the square root of negative 6. Again, so you have the square root of 54 times I over the square root of 6 times I. Again, so I can get the variable I out. And okay, and if you did not think of this combination, okay, now we have with the square root of 54. Again, 54 is not a perfect squared value, but it is the multiple of a perfect square that is greater than 1, and that perfect square is going to be at 9. Okay, so if I have like the square root of 9 and the square root of 6, square root of 9 times the square root of 6 is the square root of 9 times 6, which is 54. And I have over the square root of 6. And so we have common radical in the numerator and denominator. So we have the square roots of 6 to go out at this stage. And we have in this pathway, okay, this comes down to the square root of 9, which is also equal to 3. So you have two slightly different pathways, but both approaches are correct. And for what we have in the case of operations, and not limited to just multiplication and division, but it can also occur for what we have in the realm of adding and subtracting radicals. And let's say we have something like the square root of negative 27, and we have minus, okay, the square root of negative 300 and we have plus the square root of negative 48. Okay, so you got the square root of negative 27 minus the square root of negative 300 plus the square root of negative 48. And we have, with this trio, alright, so if I go ahead and write these terms in terms of I, so square root of negative 27, so we have the square root of 27 times I. And for the minus, okay, the square root of negative 300, we have the subtraction of the square root of 300 times I. And for the square root of negative 48, we have the square root of 48 times I. Okay, so we have all these terms are in the variable I. And now, upon first glance, all three of these look like unlike radical terms. But once we look into radical reduction, okay, it's going to turn out that we're going to be able to cluster these together as a single complex radical term. Okay, say like we have with 27, not a perfect square, and kind of like 54 earlier. Okay, the highest perfect square divisible into it is going to be 9. Okay, now for 300, not a perfect square value, but the highest perfect square divisible into it is going to be 100. And 100 goes into 300 3 times. And for 48, not a perfect square, but it is the multiple of the perfect squares with 4 at the lower end and 16 at the upper. And 16 into 48 is going to be 3 times. So the square root of negative 27, this will translate to 3 times the square root of 3i. And for the square root of negative 300, okay, you have the square root of 100, which is 10. You have times the square root of 3 times I. For the square root of negative 48, again, square root of 16 is 4. You have times the square root of 3. And we have times I. And if you notice, okay, for this trio, okay, all of these are in the letter I. Additionally, these are also in the square root of 3. And if we combine the leading coefficients, okay, so you've got 3 minus 10 is going to be negative 7. In turn, negative 7 plus 4 is going to be negative 3. And again, for the commonalities, okay, we have the square root of 3 and also I. And again, you could also express the combined result as negative 3i times the square root of 3. Okay. And now, referencing what we have with the standard form of a complex number. Again, the standard form is a plus bi. And again, a and b could be positive, or you might have a combination where one is positive, the other is negative, or where both could end up being negative. And just taking what we have in the case of standard form. Let's say if you have a complex number, we got a standard form of where we are looking at squaring. And say if you had the square of 3 minus 2i. So you have for the square of 3 minus 2y. Again, if we rewrite in terms of multiplying, okay, so we have 3 minus 2i times itself, and if I FOIL over 3 minus 2i times itself, okay, first product we have 3 times 3, which is 9. Outside we have 3 times negative 2i, so we have a negative 6i. Inside product we have negative 2i times 3, so this would be a negative 6i. And the last product, okay, you have negative 2 times negative 2 is 4. And I times I becomes I squared. And looking at simplifying, now again, for I squared is going to be at negative 1. And for what we have in the follow through, so we've got 9. Now combining negative 6 and negative 6, we have a negative 12i. For 4i squared, so we have 4 times negative 1. And as we narrow things down, okay, we got 9 minus 12i. 4 times negative 1 is negative 4. And 9 minus 4 is 5. And so the square of a standard complex number of this type, we also have to come out to yet another complex number in standard form, where we have 5 minus 12i. And now, in looking at what we can do for the next few moments, okay, in terms of working with complex numbers, and working with radicals in the mix. Okay, so if we look at simplifying the following, and let's say that we have, first of all, okay, we have, let's say we had the square root of negative 80 times the square root of negative 5 also. Let's say if we have, in terms of adding radicals, let's say we have the square root of negative 45 plus the square root of negative 125. And in the case of working with standard form, okay, say we have the square of 2 plus 3i, we have a 2 plus 3i times itself, and we'll see how that differs if you were to multiply both 2 plus 3i and 2 minus 3i. Okay, if you're still working on these items, that's fine. We have with these 4 problems. Okay, the first 2 we have with complex radical terms. Again, if you're working with complex radicals, okay, first of all, okay, rewrite them in terms of the letter I. And for what we have in the first, we have the square root of negative 80 times the square root of negative 5. Now if I had positive 80 and positive 5, I could take the square root of 80 times 5, but don't take the product whenever you have the inside numbers or any of them to be negative. Okay, so if I go ahead and write in terms of the letter I, so you have the square root of negative 80. So this will be the square root of 80i, and we have with the square root of negative 5. So we have the square root of 5 times I. Now I'll show you a couple of distinct ways to follow through. Okay, and we have with the square root of 80 and the square root of 5, I can multiply these numbers together. And we have I times I. Okay, so this will become I squared. And the square root of 80 times the square root of 5. Okay, both of these are non-negative, so I can multiply together and have the square root of 400. You have I squared, and again I can go ahead and write that as negative 1. Okay, now the square root of 400. 400 is a perfect square number. This lowers to 20. And I squared, okay, I squared is going to be at negative 1. And 20 times negative 1, okay, so we're going to have a negative 20. Okay, so this is one approach. And I'll show you another pathway. So I had the square root of 80, again, times the square root of negative 5. And rewriting in terms of the letter I, let's have the square root of 80 times I, square root of negative 5. We have the square root of 5. We have times I. And now, square root of 5 as a standalone radical term. Okay, that is the simplest form. Now for the square root of 80, okay, 80, not a perfect square, but it can be lowered. So if you looked at a radical reduction pathway in solving, so you have with 80, highest perfect square that will go into this is going to be 16. So if I split up, you have the square root of 80 is the square root of 16 times the square root of 5. And again we have times I. And again for the square root of negative 5 we had the square root of 5 times I. Now as a reduced radical term, okay, we have the square root of negative 80 becomes 4 times the square root of 5 times I. And again, from the square root of negative 5, I have the square root of 5 times I. And just clustering together, so I have the leading coefficient is at 4. And looking at the radicals, so I have square root of 5 from the first, and we have another square root of 5. And with the variables I have I times I, which will be I squared. Now just mention, we have the square root of 5 times the square root of 5, or square root of 5 times 5. So we have the square root of 25. And I can go ahead and write I squared as negative 1, which I'll do in the next step. So you got 4, and the square root of 25 is going to be at 5. I squared we have at negative 1. And in the follow through, so you have 4 times 5 is 20. In turn, 20 times negative 1 is going to be minus 20. So you have a slightly different pathway in comparison to the first approach, but it's still also a correct route where you also come out to the result in the amount of negative 20. Right. Now, for what we have in the case of the second problem, now we're looking at adding complex radicals. Okay, so here we have the square root of negative 45 plus the square root of negative 25. And now if I re-express in terms of the variable I, okay, so we have the square root of 45 times I, and the square root of negative 125. Okay, so we have the square root of 125i. Okay, so we have dissimilar numbers, and just upon first glance it looks as if you might not be able to add them together. Okay, but adding them together would be possible, but we had to reframe this, okay, to where we have expressing in terms of reduced radical terms. Now for 45, okay, 45 is not a perfect square, but in the case of perfect squares, that will go into 45, and the highest, okay, is going to be at 9. So we can say that we have for the square root of 45i, we have the square root of 9 times the square root of 5 times I. And for the square root of 125, okay, highest perfect square, they'll go into 125. It's going to be at 25. And 25 will go into 125 5 times. So we had the square root of negative 45. Okay, and that's going to become, yeah, the square root of 9, which is 3, times the square root of 5 times I. And for the square root of negative 125, okay, and having expressed in terms of the letter I, we have with the square root of 125, and this will become 5 times the square root of 5 times I. And looking at what we have in the terms, okay, so both of these, again, you have complex radicals, and lowering, okay, you have in terms of not only the letter I, but the square root of 5 times I. Okay, so you have like terms since they have the same square root radical value and also with the I attached. And if we combine the leading coefficients, okay, so we have 3 plus 5 is 8. So 3 plus 5 is 8, and we had the common attachment, which you have with square root of 5i. And so we have for this result, we can say we have 8 times the square root of 5i, or if we switch to order, we can say we have 8i times the square root of 5. Yes. Question?
When you're doing that on Alex, and you have 8i, you don't I mean, should we? Never mind. I just answered my own question.
Okay. Yeah. Okay.
Sorry.
No. I've been asked this before. You know, just to make sure. In other words, like I is never inside the radical, and that is great. You never put I inside the radical. And I've seen some, even for calculus courses, I've seen some students make that mistake. You know, so wherever you have for I, it never goes inside the radical. So what should be inside the radical should be just that number, but never the letter I. Okay. Now, for what we have with the standard form of complex numbers, okay, so we got the square of 2 plus 3i. And looking at expanding this on out, okay. So again, if you take to the second power, we're not looking at 2 times 2 plus 3i. We're looking at 2 appearances of 2 plus 3i. We're starting out the multiplication. So we have 2 plus 3i times itself. And if we look at FOILing out, okay, so you got first part, you have 2 times 2 is 4. And we got 2 times 3i is 6i. And we have also in the mix, okay, have 3i times 2 is also 6i. And 3i times 3i So this would be 9i squared. Okay, and again, we have I squared is equal to -1. And getting the result to standard form as much as possible. So you got 4, and we have 6i plus 6i will make 12i. And for 9i squared, okay, so this will be plus 9 times -1. So you have 4 plus 12i minus 9. And combining the constants, so you have 4 and -9. So this would be -5. And with the I term following, okay, so this would be plus 12i. All right. Now, for what we have in the fourth case here, okay, now we've got 2 plus 3i and 2 minus 3i. And this combination will fall into a particular category, okay, that will be referred to as conjugates, which we're going to bring up shortly. And in looking at conjugates, okay, so if I multiply together, FOIL out, so you got 2 times 2 is 4. And the outside product we have with 2 times -3i, so this will be a -6i. Inside product you have 3i times 2, so this will be a positive 6i. And the last product we have 3i times -3i, so this will be a -9i squared. And if you notice, okay, we got 4 at the front once again. However, we have with the outside and inside products. Now with the square of 2 plus 3i, I was able to combine 6i and 6i as 12i. But now we have additive inverses with -6i and 6i, so the I terms will go out. So for what we have now, we got 4 minus 9i squared. And I squared is still -1. And so we have 4 and minus 9 times -1. That's going to translate to addition. And here we have 4 plus 9. Okay, that is going to end up at 13. Okay, and I think the standalone constant will be fine. But if there was any other way, I think the textbook is picky about this. I don't think Alex quite so much. But if there was any other way, I had to put it like an a plus bi form, your a would be at 13 and your b is going to be negligible. And if there was any other way, this would be like 0i, which is still going to be 0. Now with this last combination, okay, we have with conjugates. And in terms of what conjugates are, okay, and this kind of has a feel of when we looked at factoring or forming differences of squares. And for what we have in the case of complex conjugates, okay, so we have for complex conjugates, okay, now we've had the standard form of a complex number to be a plus bi. And for a number in standard form, okay, so we have the conjugate of a plus bi is going to be A minus BI, and it works both ways. Okay, namely the conjugate of A minus BI is going to be A plus BI. And let me state this, okay, just like this particular instance, the product of complex conjugates is a constant. And just some of the samples here of complex numbers and their conjugates. Okay. And we'll have just an instance here. Okay, say we have for a complex number, okay, we have, let's say, 3 plus 5i. Okay, so we have a is at 3, and bi we have at 5i. Okay, and the conjugate, notice, okay, we're going to have, just for the number without the I, letter I attached, okay, that's going to remain fixed. Whereas in the case of the I term, we're going to have the additive inverse. So 3 plus 5i is going to have the conjugate to be at 3 minus 5i. Now let's say we have another number in standard form. Say we have negative 2 plus 7i. So your a is at negative 2, your bi we have at 7i. And again, whatever the coefficient is without the I term, the conjugate is going to have that same value. So you have negative 2, and it's with the variable term that you're going to take the opposite. So the conjugate of negative 2 plus 7i will be negative 2 minus 7i. Now let's say if I have negative 3 minus 10i. Again, you have a is at negative 3, and this will repeat in the conjugates. And again, with the complex part, we'll be taking the opposite sign. So the conjugate here is going to be negative 3 plus 10i. And say we have 7 minus 6i. Again, we have the a at 7, and we have plus 6i. Again, had the same leading term, and with the conjugates you have additive inverse I terms. And just kind of throw in a little different twist. Okay, if I have just, say, the number 5, for the number 5, okay, so 5 is just going to be referencing a, and so there's no presence of a bi entity, and the conjugate is going to keep the same value of whatever represents a. So the conjugate of 5 is going to be 5, and if I have, let's say, the number negative 20i, okay, so this will be referencing, okay, negative bi, and the conjugate is just going to be taking the additive inverse of that I term, so that's going to be a positive 20i. Okay, so these are samples of numbers and their corresponding conjugates. And just kind of referencing here what we have with the product of complex conjugates being a constant. Say if I have of like with this set here. If I have 7 minus 6i multiplied by its conjugate, okay, so if I were to FOIL out, have 7 times 7 is 49. 7 times 6i, this will be 42i. And then we have the inside product is going to be negative 42i. Last product we have negative 36i squared. And in the shape of things, okay, so we have first order I terms, namely the outside and inside products. Those are going to cancel each other. And here we have 49 minus 36. Again, you have I squared. It's going to be at negative 1. And for what we have now, we got 49. Negative 36 times negative 1 is going to be a positive 36. And the end result is going to be a constant, where the sum of 49 and 36 will be 85. And for what we have in the case of conjugates, say just for standalone variable expression. Okay, again we had negative 20i, its conjugate is positive 20i. And if I multiply together, okay, so you have negative 20 times 20 is a negative 400. I times I becomes I squared. And I squared we have at negative 1. And so we got negative 400 times negative 1. Negative times negative is a positive. And for this output, okay, we end up at 400. And in the case of conjugates, and this is going to get a little bit wordy, but I just want to mention, okay, for complex fractions, or complex number fractions, all right, so you have complex number fractions can be simplified by multiplying by 1 in the form of, okay, the conjugate of the denominator. Over itself. All right, so we have, I'll give you just a case here. Let's say we have negative 2 plus 6i. And we say we have over the letter I. So you got the conjugate of the denominator over itself. So you got the denominator is at I. Okay, so we have the conjugate of I is going to be at negative I. Okay, so looking at reducing, okay, so you have negative 2 plus 6I over I so negative 2 plus 6I over I, and if I multiply by the conjugate of the denominator over itself, so I have negative I all over negative I and distributing the case, so we have in the layout, so I have negative 2 times negative I, so we have a positive 2I, we have plus 6I times negative I, so I'm going to have positive times negative is a negative 6I squared, and for I times negative I, so we have a negative I squared. And again, I squared is at negative 1. So we've got 2I minus 6 times negative 1. And the negative of I squared, we're going to have the opposite sign of negative 1. And right now we got 2I, and negative 6 times negative 1 is going to be a positive 6. Opposite sign of negative 1 is going to be a positive 1. And 2I plus 6 all over 1. Okay, that is going to be at 2I plus 6. And if the problem is stressing, just putting in standard form, like in ALEKS, it's going to stress putting the constants in front of the variable term. So we have for this final output, we're going to have at 6 plus 2I. And that will be the final result.